What we are going to talk about today are covalent compounds. As you know, a covalent bond will form between two nonmetals. And the reason that it would form between two nonmetals is because of something we call electronegativity. As you know, electronegativity is the ability of an atom to steal electrons. Fluorine is very electronegative, meaning it's really, really good at stealing electrons. Chlorine is also pretty electronegative. It's pretty good at stealing electrons. If you're dealing with one of the metals, they are not very good at it at all. Their electronegativities are quite low. There's a big difference in the ability to steal electrons. One of those nuclei will win the electron. One of those nuclei will be able to steal an electron from the other. If your abilities are closer, if they're more balanced, let's say we have two fluorine atoms, for example, neither nucleus is stronger than the other. So instead of stealing an electron, what they're going to end up doing is sharing that electron. And when they share, that is what we are calling a covalent bond. Co together, valent for valence electrons. You are sharing your valence electrons when you have two nonmetals that combine. So let's take a look at this compound, CBr4. What we have here is carbon, which is a nonmetal, and bromine, which is also a nonmetal. The subscript next to bromine, the 4, indicates that in one unit of this compound, in one of these molecules, what you would have is 4 bromines. The subscripts, those small numbers, those are counting numbers that tell you how many atoms of each you have. As soon as you write the symbol for an element, you know there's at least one of those atoms. So for carbon, there's no number next to it. And that's because we don't have to write 1. As soon as you see the symbol, you know there's at least 1. If there was more than 1, they would tell you with a subscript indicating exactly how many more you would have, like we have for bromine. If we're trying to diagram what this molecule might look like, what we are going to do is arrange the atoms in space. The one that is least electronegative usually comes first in the compound. It's going to go in the middle. Another good clue as to what goes in the middle is that you will usually only have one of it. We have multiples of the stuff that can go around it, but we only have one of the thing going in the middle. So that's another good clue. So we've got carbon, we've got 4 bromines. I'm going to place them around the outside of the carbon. Now we've got to figure out what's happening with valence electrons. In order to determine how many valence electrons any one of these atoms have, it's going to be pretty simple. What you're going to look at is what group on the periodic table they are in. So let's take a look. So here we are at the periodic table. As you guys know, the metals are all over here and then zigzag their way down here. The nonmetals are in this corner. With respect to the nonmetals, what we know is that they tend to be very electronegative, right? We know that already. We know if two nonmetals combine, they tend to share their valence electrons. If you forget where the nonmetals are, think of a representative, right? Oxygen is a great one. Oxygen, you know it's not a metal. You can't hammer oxygen out into a sheet, right? It's in this corner, therefore the nonmetals are in this corner. The metals, which are over here, you can choose a representative for those guys too. Let's say copper, or tin, or silver or gold, or any one of these could be your example metal to remind you that the metals are on that side. If you have something from over here, we are not going to be dealing with a covalent bond. The bond we're thinking about at this particular moment is between carbon, which is right here, and bromine, which is right here. What we want to know is how many valence electrons do they have, because we want to know how many electrons do we have to play with, how many can be shared, how many are needed by each one. Bromine, which is in group 7A, right here, because it's in group 7A, we know it's got 7 valence electrons. As you guys know, in order for an element to be happy, in order for it to be more stable, it needs to have 8 valence electrons. So what bromine is going to want to do is find one more electron that it can share with someone else. So we've got bromine with 7. Carbon, which is over here in group 4, is going to have 4 valence electrons. So So let's go back to our problem and add those numbers in. All right, so let's figure out how many electrons we have to play with right here. For carbon, this is going to give us, we've got one carbon with 4 electrons, plus we've got 4 bromines, and they each have 7. So let's make sure we do this right. I'm going to go around to each bromine and give them their 7 electrons. 2, 3, 4, 5, 6, 7. What you note when I put these dots up, hopefully you can see them well on there, is that they tend to go as a group. We put 2 together. Electrons travel in pairs typically. If you see one electron on its own, like you see right here in the bromine, that's like nails on a chalkboard to a chemist. You do not want to see an electron on its own. All right? As a pair, okay, we're good, right? But once it's on its own, you know it's going to be super highly reactive because it wants to find a buddy for there. So let's check out this next bromine. We're going to place our first, second, third, fourth, fifth, sixth, seventh electrons. We still have one lone electron. Let's try this bromine. 1, 2, 3, 4, 5, 6, 7. And again, you see every single time you make a bromine, and what you have are 7 valence electrons. One of them is unpaired. For this bromine, we've got 1, 2, 3, 4, 5, 6, 7. We still have that one unpaired. And what I did when I set these up was that I left that one on its own towards the middle, facing towards the carbon, because as you know, electrons travel as pairs. So we're going to need to pair that up if we want to make a covalent bond. You can't have a covalent bond with just one electron. They will not travel on their own. So let's see what other electrons we can throw into the mix. The only element we have left to place electrons for is carbon. And carbon is in group 4. Therefore, it has 4 valence electrons. So I'm going to put one here, 2, 3, and 4. As I said before, a covalent bond involves the sharing of electrons, but you need to share at least 2 electrons, right? Because you have to have them traveling in pairs. So what I'm going to do is draw a line between these 2 electrons. That line represents a covalent bond between this carbon and this bromine. That line represents 2 electrons. So if I check out this bromine now, it has access to 2, 4, 6 electrons, sort of as their lone pairs on their own, and then 2 more in this bond. So grand total, this bromine has access to 2, 4, 6, 8 electrons, which is a full octet. That's the 8 it needs, right? So it's happy, we're good. Let's go on to this next bromine. We have a lone electron, a lone electron. What we are going to do is connect them to form a covalent bond between this carbon and this bromine. What we have now for this bromine, 2, 4, 6, 8 electrons it has access to, which is a full octet. It's more stable, it's happy. Let's check out this bromine. Again, we have a lone electron and a lone electron, which we will connect through a covalent bond. This represents the sharing of 2 electrons between this carbon and this bromine. This bromine now has access to 2, 4, 6, 8 electrons. It's stable, we're good, we can move on. Let's check out our last bromine. What we have here is 7 electrons. One of them is on its own. So what I'm going to do, create a covalent bond between bromine and carbon. That represents 2 electrons that are shared between this nucleus and this nucleus. This bromine now has access to 2, 4, 6, 8 electrons. It's much more stable, it's happy, we're good. This carbon is the last one we need to make sure has a full octet. So let's check it out. It's got access to 2, 4, 6, 8 electrons, which means it's got its full octet, and we're good. This type of structure, where you account for the placement of all the electrons, and you account for covalent bonds representing 2 shared electrons, this whole structure is something we would call a Lewis dot structure or a Lewis dot diagram. Sometimes people just say Lewis structures. Lewis dot structures, right? The dots represent the electrons, the lines represent a covalent bond. Why don't we try a trickier one? All right, so here's our second molecule that we'll be dealing with. A molecule is a covalently connected compound. Here we've got carbon. There's no number next to it. There's no subscript next to it, so that means there's only one carbon. Oxygen, there's a subscript which has a 2 next to it, meaning we're going to have to place 2 oxygens. As we learned before, it's typically going to be the element that comes first, the element that shows up once that goes in the middle. So let's put our carbon in the middle. Let's put our 2 oxygens on the outside. What we need to do next is figure out how many electrons do each of these guys bring to the table. So for that, we're going to turn back to our periodic table. All right, welcome back to the periodic table. We're dealing with carbon and oxygen this time. We looked at carbon before, it's right here. It's in group 4A. If you're in group 4A, that means you've got 4 valence electrons. If we go over to oxygen, it's in group 6A. Because it's in that group 6A, it's got 6 valence electrons. So let's see if we can place them. All right, so before we forget, let's write down how many electrons we have. It's going to be handy if you second guess yourself later and you can go back to double check that you have the right number of electrons on there. So carbon, we have 1 carbon. It gave us 4 electrons. Plus we have 2 oxygens, and they each gave us 6 electrons. So let's place these. Let's start with the oxygen. It needs 6. Okay, so what we've done is we've moved the lone electron from the carbon into this double bond, and the lone electron from the oxygen into this bond. So basically, what we have happening over here, let me fix this up, what we have happening at the moment is that the carbon has access to 2, 4, 6, 8 electrons. It just doesn't have them all the time, it shares them. Nonetheless, it has access to 8 of them, so it's going to be much more stable. It's got its full octet, we're good. Let's check out this oxygen. It's got 2, 4, 6, 8 electrons it has access to. Since it has access to 8 electrons, it has a full octet, we're good. So this oxygen, also happy. This means our structure is good. Everyone has 8 electrons, everyone is happy. This structure is quite stable. This is what would happen between carbon and 2 oxygens. They would share 4 electrons between each, 2, 4, in the form of a double bond. The oxygens would also have 2 lone pairs. Here's 1 lone pair. Here's another lone pair. Here's 1 lone pair. Here's another lone pair. And that's where all the electrons are. If we wanted to double check our work, I mentioned before that you had the ability to do that. What you do is you take a look at how many electrons you have grand total. So there's 4 from the carbon and 2 times 6, which is 12, from the oxygens. So 12 plus 4, we've got 16 electrons overall that we should have in our diagram. Let's take a look and make sure that's what we have. 2, 4, 6, 8, 10, 12, 14, 16. We are good on the electron front, we're good on the octet front, and basically that means we've done our structure right. Let's try another one. CH4. As you guys know, carbon comes first, and there's only one of it, so it goes in the middle. Hydrogens are going to go around the outside. Now, this brings up kind of a weird point. Hydrogen, although it does sort of belong in group 1, it only has one valence electron, hydrogen is a weird one. And the reason is because the electron that hydrogen has is in the first energy level. There's only 2 electrons that can fit in there. So it doesn't need 8. It doesn't need 8 electrons. It doesn't need an octet in order to be stable and happy. All hydrogen needs are 2. If you check out the first period in the periodic table, what you see is that there's just hydrogen and helium. You only need 2 electrons in that first energy level to get something that is quite stable. So these hydrogens, although they each give us 1 electron, they are only able to form 1 bond because they can only take 2 electrons. Right? It's the only element that we'll draw structures with that can do that. Everything else is going to need 8. There are a few exceptions later on, but don't worry about those for now. So hydrogen, as you know, group 1, we've got 1 valence electron. Carbon, we've checked out twice already now. It's in group 4. So we've got 1 carbon from group 4. So that means it's got 4 valence electrons. Plus, we've got 4 hydrogens, and they all have 1 valence electron. So we've placed our hydrogen as electrons. Let's place carbons. 1, 2, 3, 4. And as you guys know, a lone electron is bad, and we also need to connect all of our atoms. So let's make a connection here between these 2 electrons, here between these 2 electrons, here with these 2, and here with these 2. So now I've got 4 covalent bonds, 1 between carbon and this hydrogen, 1 between carbon and this hydrogen, 1 between carbon and this hydrogen, and our last one between carbon and this hydrogen. Grand total, each one of these hydrogens has access to 2 electrons. For hydrogen, that's enough. Hydrogen can't take any more than that. It only needs 2 in order to be set. So these hydrogens are all good. They're all stable. Carbon, on the other hand, is going to need that full octet. And so let's make sure it has it. 2, 4, 6, 8 electrons it has access to. Therefore, it is happy. It is stable. That Lewis structure looks pretty good to me. Let's double check we use the right number of electrons. 4 plus 4, we've got 8 electrons that we should have placed. 2, 4, 6, 8. We have 8 electrons that we actually placed. Therefore, this structure is good. We also have, in addition to these molecules which we've been looking at, some polyatomic ions. And as you guys know, polyatomic ions, we've got a covalently connected group that together either steals or loses electrons. So let's start with ammonia. Ammonium basically has a nitrogen, right? There's no number next to it, therefore there's only 1 nitrogen. There's 4 next to the hydrogen, so there's 4 hydrogens. And together, they end up with a positive charge. So let's figure out how many electrons we're dealing with in this particular instance. Right, here's nitrogen. It's in group 5A, therefore it's got 5 valence electrons. We're also dealing with hydrogen, which is way over here, and we just talked about it as well. It's in group 1. It's got 1 valence electron. So let's add all that up. Nitrogen, there's only 1 of it. We're going to put it in the middle. Hydrogen goes around the outside. All right, nitrogen gave us, we're 1 of it. It gives us 5 electrons each. Plus we've got 4 hydrogens. They give us 1 electron each.